Okay, so today we're going to continue doing integration using linear partial fractions. This time when we factor the denominator, it's not going to be distinct linear factors, but repeated linear factors. Okay, so let's take a look. Okay, looking at your denominator of this fraction, you're going to notice that it is x plus 2 that is being squared. So first off, we say it's a repeated linear factor because what is being repeated is x plus 2. And if you graph y equals x plus 2, you're going to end up getting a line. So that's why we call this a linear factor. Now, how many times it's repeated depends on the exponent itself. So this time it is repeated twice, okay? Not just once, but twice. So when you have to set up your partial fraction decomposition, when you have to figure out the fractions that make up this fraction that we see in our integral, you need to have the linear factor to the first power and the linear factor to the second power, okay? Because it's not just that one linear factor to the first power, distinct linear factor, and a different one, okay, to its first power, like in the last lesson. So it's a little bit of a different setup, but everything else is pretty much the same. Okay, so I had to erase some stuff and, just make this a little bit clearer to read. So we're going to use constants in our numerator because if we're describing the denominators as linear factors, whether distinct or repeated, okay, 1 degree less would be a constant. You go from x to the first, it would be x to the 0 power, 1 less, and that's 1, and 1 times any coefficient would be that coefficient. So we're going to have a and b represent our numerators. So in this particular case, let's continue. Multiply everything by the common denominator, which is the quantity of x plus 2 squared. So that's going to eliminate one of my factors, okay, when I multiply it to my first fraction on the right side of the equation, and it's going to eliminate the denominator completely like it did on the left side of the equation for my second fraction. Okay, so now I have this equation set, and I think matching coefficients would be the fastest way about this because we get ax on this side, so a has to be 6. And that means that 2a and b, which is my constants, got to be equal to 7. And if that is the case, and we know a already is 6, then we find out that 7 minus 12 would be b, and 7 minus 12 would be negative 5. So I have 6 and negative 5 as my answers. Whoop, let me erase that and actually write them in. Okay, 6 and negative 5. Now perhaps you really despise this method. You'd rather stick to a more formatted explanation for your answers. You would have to use negative 2 and some other number for x other than negative 2 to help you eliminate, because you can only eliminate a and then we can't eliminate anything for b. So let's say we do make everything for x negative 2. That's going to lead to, there we go, negative 12 plus 7, so that is negative 5 is equal to b, which is what we got. And pick anything else for x. Any integer would probably be preferable. 0 is the easiest one to work with. So if I make x equal to 0, again, any number. If you want to work with 8, that's your favorite number, I know mine is, then that will also help you solve it, okay? So we get 7 is equal to 2a plus b. We already know that b is negative 5. So we can use substitution to solve. If you end up with a system of equations, just remember how to solve a system of equations. For linear equations, you can use substitution, the addition method, you saw that in the last lesson, or even a matrix if you learned how to do matrices. So in this particular case, it's supposed to be kind of like an arrow. 7 is equal to a minus 5. So I add the 5 over, and I find that a is indeed 6. So whichever floats your boat. Okay, matching coefficients or eliminating factors, we know we can rewrite this integrand. Okay, so since my integrand is going to equal two different fractions, I'm going to take the integral of each fraction. Okay, so yesterday I rewrote it first and then broke it up. Today I'm just going to start with the breakup. Okay, so we ended up with 6 over x plus 2 and a negative 5 over the quantity of x plus 2 squared. Okay, so we can take out our factors. Okay, and if I pull out the negative 5, this is going to be minus, actually I'm missing the x, 5 times this integral here. Okay, now we already discovered, if we have like du over u as we have over here, it's the ln absolute value of u, we don't need the u substitution, so we get 6 ln absolute value of x plus 2. Now on the right hand side, believe it or not, we don't need to use ln because I can just use u substitution, of course, but rewrite this with a power of negative 2. Okay, I can't use when the power is negative 1, that's where the ln kind of comes into effect, but I can use our rules for antiderivatives if it's a negative 2. Okay. All right, I ran out a little bit of room there, so I'm going to come up here. So at this point, we already have the first one kind of done for us. We're still working on like the second part. Okay, so in order to do this, I'm going to show you with the u substitution. Once again, this is going to work out nicely. If u is x plus 2, then du is dx. So we're going to integrate u to the negative second power with respect to u. So if we add 1, we get negative 1. We divide by negative 1. So we get negative 1 over u to first, okay, because it was u to negative first power, plus c. So we're going to insert that over here, okay, but we have to remember that we're working with u. So we have to change the u back in terms of x. And let's just make this a little tidier for an answer. Okay, so we have 6 ln absolute value of x plus 2. I already said, you can move the 6 over. I don't have an ln on this side, but a negative 5 with a positive 1 is 5. So I can have a fraction. If I don't want a fraction, I can write this as positive 5 times the quantity of x plus 2 to negative first. Don't forget the plus c, so this is your answer. Okay, so hopefully you get a good grasp on using partial fractions with integration. Good luck.